Parking lot looks easy until the interviewer says design it properly. Then suddenly you need requirements, actors, classes, state transitions, pricing, tickets, and edge cases. In this video, we will solve it like a real interview. Simple terms, clear diagrams, Java code, and one useful design pattern. State pattern for the ticket life cycle. In an LLD interview, do not jump directly to classes. First clarify scope, then identify actors, then requirements. From requirements, derive entities. From entities, draw classes. Only after that, introduce patterns and code. This order makes you sound structured, not memorized. Let us define scope clearly. Our parking lot has multiple floors. Vehicles can be cars, bikes, or trucks. At entry, the system assigns a spot and prints a ticket. At exit, it calculates the fee and marks the ticket complete. We will keep pricing simple, hourly pricing by vehicle type. We will not design subscription passes, QR payments, valley parking, or city scale parking discovery. Mentioning what is out of scope is a good interview habit. Actors are simple. The driver enters and exits. The entry gate asks the system for a spot. The exit gate calculates payment. An admin manages floors and spots. An attendant handles special cases like lost tickets. This diagram is useful because it separates human roles from system responsibilities. Functional requirements are what the system does. Park a vehicle, unpark a vehicle, track free spots, calculate fee, and handle lost tickets. Non-functional requirements are quality constraints. Spot lookup should be fast. Booking should be thread safe. Pricing should be extensible. Ticket history should be auditable. This split impresses interviewers because it shows design maturity. This is a simple data model. A parking lot has many floors. A floor has many spots. A vehicle receives a ticket. A ticket is assigned to one spot. When the driver exits, payment is attached to the ticket. In LLD, you do not always need a full database design, but showing a clean ER sketch helps you think about persistence. The class diagram follows directly from requirements. Parking lot is the main service. It delegates spot search to floors. Parking spot knows whether it is available and can be occupied or freed. Vehicle stores number and type. Ticket stores entry time, assigned spot, and current state. Pricing strategy keeps pricing flexible. Ticket state gives us clean behavior for paid, lost, and exited states. This is the happy path. The driver reaches the entry gate. The gate scans the vehicle. Parking lot asks floors for an available spot. The floor reserves a suitable spot. Then the system creates a ticket and returns spot ID plus ticket ID. In code, this must be thread safe because two cars can enter at the same time. Why state pattern? Because ticket behavior changes based on its state. An active ticket can be paid. A lost ticket needs a penalty. A paid ticket can exit. An exited ticket should not be paid again. If we put all of this in if-else blocks, parking ticket becomes messy. State pattern moves state-specific behavior into separate clauses. Without state pattern, ticket logic becomes a pile of if-else statements. If active, do this. If lost, do that. If paid, do something else. That works for two states but breaks as rules grow. With state pattern, each state owns its behavior. Active ticket state handles pay. Lost ticket state handles penalty. Paid ticket state handles exit. The code becomes easier to extend. Start simple. Vehicle type tells us whether it is a bike, car, or truck. Spot type tells us whether spot is small, medium, or large. Vehicle has a number and type. In an interview, simple immutable models are better than over-engineered models. You can always add owner, color, or registration later. Parking spot holds the current vehicle. The key detail is synchronization. If two entry gates try to assign the same spot at the same time, this method protects us. In a real distributed system, you would use database loss or transactions, but for LLD, synchronized methods are enough to show the concurrency concern. Here is the state pattern in Java. Ticket state defines allowed operations. Active state allows pay but blocks exit. Paid state blocks duplicate payment but allows exit. The ticket delegates behavior to its current state. This avoids if else inside parking ticket. The park method is intentionally boring. Find a spot. If no spot exists, throw parking full. Occupy the spot and create a ticket. The important design choice is separation. Parking lot coordinates, parking flow searches. Parking spot handles occupancy. That is how you keep responsibilities clean. If the interviewer asks about database tables, keep it simple. Spot store ID, floor ID, type and status. Ticket store vehicle number, spot ID, entry time, exit time, and state. For concurrency in a real DB, you'd reserve a spot inside a transaction. Again, do not overbuild unless the interviewer asks. These are the edge cases interviewers expect: parking full, lost ticket, two gates trying to assign the same spot, vehicle trying to exit without payment, broken or reserved spots, different pricing by vehicle type, ticket already exited. If you bring these up yourself, it signals that you think beyond the happy path. Final formula: requirements first, then actors, then entities, then classes, then patterns only where they solve a real problem. For parking lot, state pattern is useful. For ticket lifecycle, Java code should be simple, readable, and responsibility driven. Do not memorize parking lot. Learn the design flow.